is everybody today? Good. Okay. Today we're starting a new chapter. It goes over pi conjugation. So we're going to be looking at this chapter at pi-electrons and what those pi-electrons can do other than just sit in a pi orbital. So the three concepts we're going to cover in this chapter are conjugation, resonance, and aromaticity. You've probably heard of some of these terms before. You might not know exactly what they are. So we'll go over these terms. Chapter 5. Chapter 5. Yeah, chapter 5. So we're going to start off by investigating the molecule 1,3-butadiene. Right? You can see that 1,3-butadiene has carbon-carbon double bonds. It also has carbon-carbon single bond. Right? And so we're going to just identify the average bond length that we would expect for a carbon-carbon single bond, carbon-carbon double bond. Do you know what these are? These are things you have to know. So carbon-carbon single bond is going to be about 1.54 angstrom, right? Or 154 picometers. Carbon-carbon double bond, that's going to be about 1.32 angstroms. Right, so we learned yesterday, many of you learned yesterday when we went over IR spectrophotometry, that double bonds are shorter and stronger than single bonds, right? And so this trend holds. Okay. When we look at 1,3-butadiene, the actual bond lengths for 1,3-butadiene are 1.47 angstroms, and for each of the double bonds, 1.34 angstroms. All right, so if we pay close attention to these numbers, right, 1.47 angstroms, that's shorter than a standard or an average carbon-carbon single bond. Okay, 1.34, it's a little bit longer. Than an average carbon-carbon double bond. Right, what we learn when we investigate this system, the electronics of this system, is that the double bonds on the end, they're not really full double bonds, even though we draw them that way, right? They're not really full double bonds. Right? And the single bond in the middle, it's not really just a full single bond either. Right? The single bond in the middle is going to have some double bond character, right? And the double bonds on the end are going to have some single bond character. And to really understand this, the structure, we have to pay attention to the pi electrons. Right, so we're going to look at the pi molecular orbitals of 1,3-butadiene. If we look at 1,3-butadiene, what's the hybridization of each carbon in that molecule?
There are two
Good. Right. All 4 carbons are sp2 hybridized. Right? Meaning all 4 carbons have to have a p orbital. Okay? A p orbital, as we've shown it here, right? Each p orbital is bonding to an adjacent p orbital to make a pi bond. Right? So each of these carbons must have a p orbital. Right? On the structure that we draw, right, we have 4 p orbitals in a row. On the structure that we draw, we show an overlap between the p orbitals on carbon 1 and 2, right, and the p orbitals on carbon 3 and 4. We have to understand on carbons 2 and 3, there are 2 p orbitals we're not showing any overlap with. And that doesn't really make sense, right? That a p orbital on carbon 2 would only overlap with a p orbital on carbon 1, right? Not have any overlap with p orbital on carbon 3. Why would a bond to the left, right, not make any bonds to the right? Okay? And so what this suggests is that the structure that we draw for 1,3-butadiene is not completely accurate of what's really going on in that system. Right? Because we can't have a p orbital that completely ignores one p orbital, right, overlaps with the other p orbital. Right? And so this takes us to drawing the pi molecular orbitals in 1,3-butadiene. Right? So when we think about molecular orbitals, when these 2 p orbitals overlap, how many molecular orbitals are going to be formed? Not a question. Yeah.
With those 2, 1 pi.
Okay, 1 pi bonding orbital, and
1 sigma.
not sigma. Pi antibonding orbital. Right? Remember, we take 2 atomic orbitals, we overlap them, we always create 2 new molecular orbitals. One is bonding, and one is antibonding. Right? So with pi orbitals, just like with sigma orbitals, we create a sigma bonding orbital, sigma antibonding orbital. Right? With pi, you create a pi bonding orbital and a pi antibonding orbital.
So would you need both the sigma and the pi, like bonding and antibonding?
No.
A double bond?
What do you mean? Would you need both of them?
Or like, would you count for both since a pi bond is made up of sigma and pi?
Sure. So yeah. So let's draw out just a really simple system first. That's a good idea. Right. So if we just take a look at ethene. Right, and try to understand this from a molecular orbital perspective. Right, we have our 2 carbons. We have our sigma bonding orbital. Right? And then we have our sigma antibonding orbital. Okay, so the overlap of the would be an sp2 orbital on this carbon with an sp2 orbital on this carbon, right? The 2 atomic orbitals overlap to produce a sigma bonding orbital and a sigma antibonding orbital. All right, questions about that? Went over that the other day. Right. There's also p orbitals on these carbons, right? So when these p orbitals overlap, they will overlap to produce a pi bond. same time, right, those p orbitals will overlap, those p orbitals overlap to produce a pi bond. They're also producing a pi antibond, right? So the pi bond comes from the in-phase overlap of p orbitals. Pi antibond, or pi star, comes from the out-of-phase overlap of p orbitals. Right. The principle is the same. We take two atomic orbitals, we overlap them, we produce two new molecular orbitals, right? So it's just a matter of identifying what those initial atomic orbitals are. Any questions about that?
Which ones are like associated with each other? You know what I mean? Like which is colored in and non-colored in, like for each side? Is like the top two associated with each other, or is it each side is associated?
So the color shows the phase, right? And so we take two sp2 orbitals. Right, that's going to be the in-phase overlap of the sp2 orbitals, producing the sigma bond in between. Okay. The out-of-phase overlap of sp2 orbitals, right, it's going to look like that. Okay, and that's what produces the sigma antibonding orbital on the outside, right? So these two lobes that we're showing, part of the same orbital, just one orbital, right? Just kind of separated into two different volumes of space. The fact that I shaded in one area to the left just indicates the out-of-phase overlap, okay? When p orbitals overlap, this represents the in-phase overlap of p orbitals, right? So both top halves are shaded, both bottom halves are not shaded, right? And so that would produce a pi bond, right? And so this is one pi bond. Two electrons can exist in the top or the bottom, right? It's just one volume of space, even though it's separated into two separate states, right? And then the pi antibond would be the outer phase overlap of those p orbitals, right? So on one p orbital, we would have the top half shaded. On the other p orbital, we would have the bottom half shaded, right? And now these four volumes of space represent the pi antibody. Okay. They're in the same plane as the pi orbital. I mean, they basically look like the p orbitals that we started with, just the p orbitals trying to get away from each other. Right? Yeah.
So then why is it the top part of the pi one not shaded and the bottom is? Like, would that just mean like it was supposed to be in?
It's just indicating how those p orbitals combined, right? So when we draw p orbitals, one half of the p orbital is shaded, right? One half of the p orbital is unshaded. And that's just to indicate the node in the middle, right? So the in-phase combination would be either both top halves are shaded or both bottom halves are shaded. It doesn't matter which we represent. And so again, this is just indicating where the node in that system is, right? That helps? Yeah. Okay. Other questions? Yeah.
So in that molecule, the 1,3-butadiene, is one of them in phase bonded in phase, one of them is bonded out of phase with the double bond?
That's what we're gonna look at next. Yeah. All right. So to understand the bonding in just ethene, right? We draw the sigma orbital and we draw the pi orbital. Okay. In terms of the higher energy electrons, right? The pi electrons are going to be higher in energy, farther away from the nuclei, right? Not as stabilized typically. Right? So when we're looking at the pi molecular orbital of ethene, we're paying attention to the p orbitals that overlap to form that pi molecular orbital. When we look at the pi molecular orbital in 1,3-butadiene, we have to realize that, again, we have 4 p orbitals in a row, right? And p orbitals can't, ignore a p orbital that's next to it. Even if we draw it like we do up here, right? The p orbital on carbon 2 can't just ignore the p orbital on carbon 3, right? And pay attention to the p orbital on carbon 1. It doesn't work like that. right? So if we have four p orbitals in a row, they can all overlap, essentially, right? If we're starting with 4 atomic orbitals, when they all overlap, eventually we'll be able to form 4 new molecular orbitals, right? So just like we're taking 2 atomic orbitals here and forming 2 molecular orbitals, here we're taking 4 atomic orbitals, they'll overlap, will form 4 new molecular orbitals, right? And so that's what we're going to draw here, where those pi electrons are and are not in 1,3-butadiene. Okay. So, right, these are each p orbital is supposed to represent a carbon in 1,3-butadiene. Right, so this would be carbon 1, carbon 2, carbon 3, carbon 4. Right, you can draw 1,3-butadiene down here on the bottom. Right, 4 p orbitals. We're going to have 4 molecular orbitals, and we're going to identify them as psi1, psi2. Psi3, and Psi4, right? And I've drawn these vertically to show that the lowest orbital that we have drawn is going to be the lowest in energy, right? And the orbital up top, that's going to be the highest in energy. Okay? So, lowest energy orbital, when these orbitals overlap, they're going to overlap all in phase. Right. Every time we move up in energy, up one orbital, we gain a node. Right, and this is just equivalent to a node on a p orbital, right? So between if you have a 1s orbital, right, just a sphere, a 2s orbital is going to be bigger, right? And in that sphere, there's going to be a area where electrons can exist, right? So electrons can exist, say, on this side of that dotted line, it can exist on this side of the dotted line, right? But it can't exist in that dotted line. That's one node, right? As we go from shell 1 to shell 2, we gain one node. You see that node in the 2s orbital, right? We see that node in the 2p orbital. Okay, so same thing here. When we go up one energy level, we're going to gain one node. Right? And all this node is showing is that there's an in-phase overlap between carbons 1 and 2, in-phase overlap between carbons 3 and 4, right? But an anti-bonding or out-of-phase overlap between carbons 2 and 3. Right? So just like we gain a node when we move up in energy levels on these atomic orbitals, we'll gain a node when we move up in energy levels on these molecular orbitals. Questions about this? Right, how many nodes do you think is going to be in psi3, the third molecular orbital? Good, 2 nodes. Right? Right, so the nodes just depict out of phase overlap or anti-bonding overlap. Right, so we'll have an out of phase overlap between carbons 1 and 2. 2 and 3 will be in phase. And then 3 and 4 will be out of phase. Right, and how many nodes in psi 4? 3 nodes. Right, so that just means that there's an out of phase overlap among all orbitals. Okay, so this is our molecular orbital diagram. We don't have any electrons in here yet, so we've got to put our electrons and figure out where the electrons are among these 4 orbitals. So how many pi electrons are there in 1,3-butadiene? Six.
4.
4? How do you know there are 4?
Because there's 2 double bonds.
Good. 2 pi bonds, right? Each pi bond is going to have 2 electrons, so there are going to be 4 pi electrons total, right? Or we can think about it if we have 4 p orbitals, each p orbital has to have an electron, right? If we're distributing electrons equally among all orbitals around the carbon. Okay, so 4 electrons among these orbitals, where are we going to put those electrons? Go ahead.
In phase overlaps?
So I mean, we're just filling these orbitals. We're not saying where right now, what p orbital those electrons are in. We're just filling these orbitals, right? So we can, we have 4 orbitals. Which orbital will we fill first?
First.
Right, lowest energy orbital, right? Not a trick question. We always put electrons or fill the lowest energy orbitals first, right? So we'll put 2 electrons there. What orbital are we going to fill next? Psi 2. Right, second energy orbital, Psi 2. All right, now we're out of electrons. Okay, so what is this telling us? This is giving us a map of where those electrons are and how they're being shared, right? We have 4 pi electrons in 1,3-butadiene. Those 4 pi electrons are going to be isolated to these 2 molecular orbitals, right? The 2 electrons in psi 1, where are they in that molecule? According to this, what we see here in the molecular orbital, where are those 2 pi electrons? You know? Right?
Above them all. So.
No. I mean, they are. They can spend some time there, yeah.
Would they be in the non-colored region of the pi orbital?
They can spend time there too. Not isolated there. Anybody else want to give some information? Okay, so what this is showing, right, whenever we have a pi bond, right, we have in phase overlap of those p orbitals to form the pi bond, right? The electrons in this pi bond can be up here, right? Or they can be down there, right? One can be on top, one can be on the bottom. They cannot be in the middle, right? That's where the node on the p orbital is, that's where the node on the pi orbital is, right? But anywhere in this shaded area, anywhere in this clear area, those electrons can exist, right? When we look at psi 1, there's in-phase overlap among all 4 orbitals, right? So if we wanted to draw a p orbital, or sorry, a pi orbital representing that overlap, right? All we would show is that those p orbitals are all overlapping to form one big pi bond, right? And so these 2 electrons that we have in this molecule, these 2 pi electrons in the lowest energy orbital, they're going to be shared equally among all 4 carbons. Okay, that's what this low energy orbital is telling us when we draw it out. Right? There's no anti-bonding orbital among those p orbitals, or sorry, no anti-bonding interaction among those p orbitals. Right? So those 2 pi electrons are free to roam among all 4 carbons. Doesn't matter. Okay, questions about that? Okay.
Even though between carbons 2 and 3 there's no double bond, it still just goes back and forth.
There's no double bond when we draw it like this, right? But the molecule, we have to understand, electronically is going to look way more like this, right? I mean, this is just lines, right, that represent 2 electrons. But those lines, I mean, if we look at a molecule under a powerful enough microscope, we can actually see the big electron clouds that are formed, that are held by orbitals, right? And so the lowest energy orbital is going to have 2 electrons and be shared among all 6 carbons. And that kind of reconciles what we see here, right? If this is a true single bond, we would expect it to be around 1.54 angstroms. The fact that that's significantly lower than 1.54 tells us that there's some pi bonding or double bond character between carbons 2 and 3, even though it's not illustrated in this structure, right? We can better understand that. Does that make sense? Other questions? Yeah.
Where does the electron come from?
The electrons?
Yeah.
From, if we think about sp2 hybridized carbon, right? Carbon has 4 valence electrons, sp2 orbital, sp2 orbital, sp2 orbital, p orbital. Right? Each of the electrons is going to be isolated to 1 orbital. If we think about just, again, carbon, we can't isolate as just an atom, and so we rationalize its atomic structure by how it bonds, by what we see in molecules. Right? So 4 valence electrons, 4 orbitals around carbon. Each orbital gets an electron. Yeah.
So just to clarify, are you saying that there would be 2 electrons that are shared across all 4 carbons, and then equally there would be 2 electrons shared just between 1 and 2?
Awesome. Yeah. Right. So the next orbital that we fill is psi 2, right? And so what these electrons, or what this orbital is showing, is that those electrons can exist between carbons 1 and 2. Those electrons can exist between carbons 3 and 4, but they cannot exist between carbons 2 and 3. There's an anti-bonding interaction there. Okay. So this is telling us that even though we draw the molecule like this to show 2 pi electrons here, 2 pi electrons there, that's not the true picture of 1,3-butadiene. Right? These double bonds. Referred to as being conjugated double bonds, or the electrons being conjugated with each other. Right? And they're all going to be connected by p orbitals. Okay, so again, this gives us a much clearer picture of where the electrons are, right? And it helps us understand kind of some of the physical attributes of 1,3-butadiene, right? We no longer see these as just isolated pi systems, but as conjugated pi bonds that can talk to each other. We're better off. All right, questions?
So with the chart you drew there,
Yeah.
I guess I'm struggling about how many electrons are in each of these. So for 2 of the, I guess, infinity-like signs, is that equal to 1 electron above in the chart? So like
This thing here?
Yeah, when they're all in phase,
Yeah.
does that show 4
So this is just an orbital, right? We're just drawing a p orbital.
An orbital that an electron will.
An orbital that an electron will occupy, right? So if we think about just, again, we don't have carbon atoms, right? We understand carbon by looking at how it bonds within a molecule, right? So if we're gonna locate the electrons around an sp2 hybrid carbon atom, right? 4 valence electrons, we're going to put 1 electron in each orbital, right? So in ethene, say, right? In order for this carbon to bond to everything, right? It's using an sp2 orbital to bond to hydrogen, needs 1 electron there. An sp2 orbital to bond to the other hydrogen, needs 1 electron there. sp2 orbital to make the sigma bond to carbon, needs 1 electron there. And then a p orbital to make the pi bond to carbon, so it needs 1 electron there. All right, so when we're looking at 1,3-butadiene, each of these carbons is going to have a p orbital, right? In order for this pi bond to form, it needs 1 electron from this p orbital and 1 electron from that p orbital.
Okay.
All right, so we're just drawing those 4 p orbitals, kind of ignoring how we drew the bonding pattern in the structure up here, and saying, all right, each of these has 1 electron. How can these 4 orbitals combine? In the lowest energy, right, they're going to combine all in phase. We have 2 electrons, or 2 electrons in this case, all right, and they are going to occupy this whole area, right? There's no connection that they can't occupy.
Okay, so these represent the carbons in the whole.
These represent the carbons, in the molecule and the p orbital specifically.
Okay, got it. Thank you.
Good. Other questions? All right, so in this diagram, we can identify psi1 and psi2 as bonding orbitals. Right, and generally psi3 and psi4 then as anti-bonding orbitals. Okay, psi3 and psi4 right now we don't really have to care about because there aren't any electrons in them. It's good to know how to draw them, but no electrons, so we don't have to locate anything in those systems. Okay, so I want to talk about how to identify conjugated pi systems. You have to have repeated pi and single bonds. Right? But you have to make sure that those pi bonds have the correct relationship with the sigma bonds. So here are two systems. You can see both of them have repeating pi bonds, right? Only the system up top is conjugated. Right? The system down at the bottom is not conjugated. Why would the system at the bottom not be conjugated?
Because each double bond is separated by two single bonds.
Good. Each double bond is separated by two single bonds, right? And importantly, we have these sp3 hybridized carbons that aren't going to have a p orbital that allow those pi bonds to communicate with one another. And if we look at the conjugated system, all of the carbons are going to be sp2 hybridized. And so all of the carbons are going to have a p orbital. Right, yeah.
So if you had an SP where it has two p orbitals, would you just do the same thing but multiply it by 2?
No. So it's a good question. Okay, so here's an example of a conjugated system with a triple bond. Okay, that triple bond consists of two pi orbitals, right, and one sigma orbital. But only one pi orbital is going to be in conjugation with the rest of the system. Why would that be?
Because with the SP2s, all the p orbitals are oriented up instead of the horizontal.
Good, right? In order for the p orbitals to talk, they have to be oriented in the same direction, right? If we had one set of p orbitals on this plane and one set of p orbitals on this plane, right, those p orbitals would not be able to be conjugated, would not be able to talk, right? So in this triple bond, we have two sets of p orbitals on two different axes, okay? And only one of them is going to be able to align with the rest of the pi system, right? So this triple bond is in conjugation, but it's in conjugation because of only one pi orbital, not as opposed to pi orbitals. All right, this is why geometry, we spent a good amount of time talking about geometry, right? The bonding geometry, the electron geometry around the center. This is why it matters, right? Those electrons just aren't anywhere we want them to be. Question?
So we would say that this isn't conjugated?
This is fully conjugated, yeah.
Oh.
Fully conjugated system. Right? We're assuming, say that it's the green electrons, right, that line up with all the other. Right, so it's this pi orbital here that would be in conjugation, and the pi orbital would be isolated by itself. Other questions?
How can you show the green pi, or you show the green orbitals there, but then on the one above it, the conjugated pi bond one, the carbons on the end don't have the.
I just didn't drop them in.
Oh, okay.
Yeah. Other questions?
So first one and the second one you earlier.
Yeah.
So there were like sp3 carbons present.
Yeah.
Is that only when they're like between the pi bonds that would not be conjugated, or
Correct,
is there
yeah.
one of the other?
What's that?
Like there's a
There's an sp3 here.
Yeah.
Yeah, on the end.
Okay, so it doesn't matter.
I mean, it's not going to, if this was sp2 for whatever reason, it would just extend the conjugated system.
Okay.
But if it's sp3, it just means that the rest is conjugated without that.
Okay, that makes sense.
Makes sense?
Thank you.
Yeah. Other questions? Yeah.
So when you're looking at the triple bond diagram, and like if you wanted to draw a chart for it, like you do to the right side, would you just not count the blue bonds, like you would just count up the green?
Yeah, so if we want to make this a little simpler, so here's equivalent to 1,3-butadiene, right? We just have, rather than a double bond at both ends, we have a double bond at one end and a triple bond at the other end. The system is still fully conjugated, right? So all 4 carbons, or the 4 pi electrons are conjugated with each other, right? It's just going to be the electrons, pi electrons in the blue orbital, right? The green orbital, the green p orbital is not overlapping with anything but itself. Okay, so that pi bond would not be conjugated. Okay.
If we were, I mean, obviously you don't have to, but like if we were to just draw up the chart for like the top 2 examples, would we have like 10, like of the instead of just having 4? Like how you have to.
Correct. Yeah. So you have to draw out a lot of these. So I don't know if it's in this book or another one, but there is a diagram for 1,3,6-hexatriene, right, where we can identify where the electrons are in that system. Same thing, 1,3,6-hexatriene, right, we're going to have 6 p orbitals, psi 1, all 6 p orbitals are going to be in phase overlapping, right? Psi 2, we're going to have 1 node, psi 3 will have 2 nodes, psi 4, 3 nodes, right, and on up to, we have 6 total orbitals. Yeah.
So if we were to draw that big chart, then wouldn't it be like we get to such high? Oh no, there's only 4 nodes possible still.
So so here there are 3 nodes, right? We have 4 p orbitals. So in a 6 p orbital system, there would be 5 nodes.
Wouldn't it be such high energy that it just wouldn't? Why would it ever go up to 5 nodes?
Yeah, so remember, it's not so much about the orbital energy. I mean, orbitals themselves don't have any energy. It's the electrons that have an energy in those orbitals, right? So if an electron is not in an orbital, we don't have to worry about that energy, right? We put them in this order because, in theory, if there was an electron up here, right, this would be the energy level. But the electrons are isolated to psi 1 and psi 2. Right? Same thing with 1,3,6-hexatriene. Pi bond electrons would be isolated to psi 1, psi 2, and psi 3. So 4, 5, and 6, even though they're high in energy, right, it would be an electron that would be high in energy that would, if they're in that way. But no electrons in it. Okay. Other questions? We'll stop there. Thanks for asking lots of questions today. We'll come back. If you have a chance to read through chapter 5, it would be helpful just so you can get some context. The pictures in the book are better than the pictures that I can draw in the book.